we're going to shift our attention over to unconventional gas reservoirs. Several unconventional gas plays in the United States have come online and have significantly increased gas production there. We'll talk about tight gas sands and gas shales during this part of the presentation. Tight gas sands are the first tier of unconventional resources. They are like conventional reservoirs, but they have been compressed and compacted and have lost their permeability. An example of a very successful tight gas sand development is in Jonah and Pinedale fields in Wyoming. These fields produce out of the Lance Reservoir, which is a very thick, about 2,000 feet thick, low permeability reservoir that is found at depths from 8,000 feet to 14,000 feet and deeper. Because of these depths and the thickness of the reservoir, these fields were developed with vertical wells. The fields also were originally developed on 80-acre spacing, or 8 wells per square mile. The well results were very good, and so the operators wanted to downspace or drill wells at closer spacing because that could lead to doubling the number of wells that could be drilled. Operators in unconventional reservoirs are constantly trying to determine the closest well spacing that can be economically drilled. After several phases of downspacing, now these two fields are being drilled at 5 to 10 acre spacing, or 64 to 128 wells per square mile. And to put things in perspective, the squares that you see up here on this map are 6 miles by 6 miles, or 36 square miles. So with this concept of downspacing, the operators have been able to prove up hundreds of additional locations remaining for development. So shown here are the graphs of historical production and well count for tight gas reservoirs in the Rocky Mountains, two of which that we've already talked about, Jonah and Pinedale fields, as well as the Mesa Verde Reservoir. The Jonah fields in the upper left and the upper right is Pinedale, and at the bottom is the Mesa Verde Reservoir. The Jonah field is currently producing about 600 million cubic feet per day. Pinedale is at about 1.4 BCF per day, and the Mesa Verde is about 1.1 BCF per day. In the graphs, you can see the well count impact on production and the issues that can occur with downspacing. For example, in Jonah field, if you look at the well count continues to increase, but production continues to decrease. And so this illustrates that with downspacing, the wells can end up being less productive. And this picture shows an outcrop of a shale reservoir. This is the Woodford Shale in southern Oklahoma. Outcrops show some of the physical characteristics of shale reservoirs. You can see the layering of this reservoir and some natural fractures that exist in the outcrop. And this illustrates that this shale is brittle and is a good candidate for fracking. So this slide discusses the calculation of gas in place for gas shales. The picture on the left shows the large thickness that's covered by available for production in the shales, and the methods that operators use to develop these reservoirs. You can see the vertical wells tap into a small amount of the reservoir. They contact a small amount of the reservoir, and the horizontal wells, still in that picture, contact a much greater part of the reservoir. They have much more contact with the reservoir. It is like having multiple vertical wells in the reservoir along the lateral portion of these horizontal wells. The box on the right shows the large area of the shale that can be developed with horizontal wells. Then we show the gas in place calculation for shales at the bottom of the slide. Area times thickness times organic richness and porosity yields gas in place. And this is a physical example of the Barnett Shale that was taken from the subsurface and brought to the surface. It was then placed in a glass of water, and after a few days, gas bubbles formed on every surface of the shale and started to bubble off the shale. And this illustrates that there is a lot of gas sitting in the shales, and because of low permeability of these reservoirs, an operator wouldn't be able to produce this gas without performing some sort of fracture stimulation, without inducing permeability. So this map shows the various locations of shale projects that Netherlands Sewell has had the opportunity to evaluate throughout the world. The many stars in the United States illustrate that the dominance of commerciality of shale is located in the United States. In the United States, also infrastructure is available, similar to what Al mentioned. Service companies and equipment are available to facilitate shale development, and also public reporting of production allows companies to assess the estimated ultimate recoveries of shale wells and determine the statistics in these shale plays. And we are fortunate to have worked many projects in the United States in the shales that exist there, and we can leverage our expertise from this onto shales that exist internationally. We've also worked on projects in China whose volume of shale gas potential we'll discuss on the next slide. This slide is a little bit busy. On the left-hand side, you can see a table from an EIA report, and this table shows gas balance, both production, consumption, and imports, as well as proved gas reserves and shale gas resources of countries located throughout the world. In this table, the column header for the column furthest to the right states technically recoverable shale gas resources in TCFs. So shale gas resources may exist in these countries, but this reflects potential only. Their commerciality is uncertain, and these gas resources may or may not be developed. On the right-hand side, we've listed out the from high to low of the top 10 countries of the technically recoverable shale gas resources. You can see that China has the most shale gas potential per this EIA study, and China is followed by the United States, and then there are other countries in different parts of the world that follow these two countries. Also of note is that more than 30,000 horizontal shale wells have been drilled in the United States, and excluding Canada, where several thousand horizontal wells have been drilled, less than 100 horizontal wells have been drilled in other parts of the world. This map shows emerging and developing oil and gas shale plays in North America, with the size of the star indicating relative production amounts from each shale play. Key fields include those that are termed the Barnett Shale, the Fayetteville Shale, the Eagle Ford and the Bakken Shale, the Marcellus Shale in the northeast of the United States, and the Woodford Shale. And these all produce large volumes of oil and or gas relative to other shale plays on this map. And this is a map of northwestern Europe, with the red outline within Germany being the aerial extent of the Barnett Shale. The Barnett Shale, as Scott mentioned, was the first shale gas that was commercially developed in the United States. What this represents is the large area that the shales can cover. And this graph shows a completion chronology within the Barnett Shale. Operators started first drilling vertical wells using an older gel-based frac technology, and the initial production rates from these wells started at about 700 MCF per day. Then in 2001, operators changed up the frac technique and used a new slick water frac technique, and initial production rates approximately doubled to about 1.4 million cubic feet of gas per day. This doubled the production rate. Operators also applied this frac technology to the wells that had been fracked with the old style frac technology, and were able to achieve higher rates than were previously observed in those wells. Then in 2004 and 2005, operators started to apply horizontal drilling techniques, and these wells that were drilled horizontally and fracked achieved initial production rates in excess of 3 million cubic feet of gas per day. And then since 2007 to present, companies are starting to use batch drilling and completion techniques and are bringing online multiple wells at the same time. In this example, they are bringing online close to 9 million cubic feet of gas initial rates from these three wells. And this is a picture of the trajectory of a typical horizontal well in an unconventional resource play. Operators will drill a pilot hole to a certain depth, and then will switch out the tools that they're using to drill, and will use special tools to build angle to drill into the target shale zone. Then multiple stages of fracture stimulation are performed to crack open the reservoir. This creates permeability and makes it easier for hydrocarbons to flow from the reservoir into the wellbore. And you can see in the lower left the fracture stimulation stages. There are multiple stages, and you can also see that the fracture stimulations don't propagate too far away from the wellbore. Another few items to note include that there's a layer of casing separating the wellbore from the groundwater that's at the surface or near the surface. And also it's important to note that the shale gas reservoirs are about 2,000 to 4,000 meters lower than where typical groundwater aquifers are located. And this slide illustrates the impact of spacing on recovery per well and recovery overall of unconventional reservoirs. As I mentioned, operators are trying to determine the optimal spacing that they can economically drill that is able to maximize recovery of the reservoir. So in this theoretical example, on the left-hand side, you can see a development at 80-acre spacing, which yields slightly higher than 5 BCF per well at 35% recovery factor of the gas in place of that area. If the spacing between the wells is cut in half to 40 acres per well, then the recovery per well goes down to 4 BCF per well, but the recovery factor of the reservoir of this area of the reservoir increases to 50% of the original gas in place. And this slide illustrates the components of a successful shale play. There's a lot of science that can be done up front to try to understand the different characteristics of the shale and the hydrocarbon potential of the shale. Most important of these, as you can see in the center of this page, is productivity of the reservoirs. What is very important also is having a good statistical database of EURs to assess the commerciality of the shale plays. Assessing the economics in international shales becomes more difficult because with less infrastructure and less service companies and equipment, the cost is higher. And because there are fewer companies developing shales in international areas, there is less activity to report. There's less data available to assess the commerciality of shales for new entrants. And this slide identifies what to consider for shale gas evaluations. It is important to understand the reservoir and geologic characteristics and parameters of the shale. These are characteristics that the operator doesn't have any control over. Then in order to optimize the value of the shale gas reservoirs, it is important to control or have a good understanding of these other issues, which include where are the sweet spots of the shale located. Not all parts of the shale are created equal even within the same field. What well spacing should be used? How many fracture stimulation stages should be applied to the wells? Do the wells need some sort of pumps or artificial lift in order to produce optimally? Then what are the capital costs and the operating costs associated with the shale play? These are inputs that have significant impact on the commerciality of shale gas reservoirs. So the title of this slide is Fracture Stimulation, Shale Gas is Easy. So essentially the message that we're trying to communicate there is that this picture of the destroyed frac trucks illustrates that it will take a lot of effort to get shale gas out of the ground and may even wreck a few frac trucks.